$125 million in engineering, 9 months of flawless flight, destroyed not by an explosion, not by a hardware failure, but by a math error so basic it would not pass as a homework problem. A spacecraft that crossed hundreds of millions of miles to reach Mars was gone in an instant. And the most unsettling part? Every single system said everything was fine. Mars had always been a world of questions. By the late 1990s, NASA was determined to get answers. The Mars Climate Orbiter was designed to be the eyes and ears in orbit, scanning the planet's thin atmosphere for secrets no one had ever seen. Its job was to map temperature, pressure, and water vapor patterns, to track dust storms that could swallow cities, and to deliver daily weather reports from 140 million miles away. This was not just science for science's sake. The data would shape the future of every rover and lander that followed, missions that would depend on knowing when a single gust of Martian wind might tip the odds. The spacecraft itself was a marvel of precision. Built by Lockheed Martin in Denver and guided by the Jet Propulsion Laboratory in Pasadena, it was the centerpiece of NASA's Mars Surveyor program. The price tag was $125 million, a sum that bought 9 months of careful planning, thousands of hours of engineering, and a launch window that would not come again for over 2 years. On December 11, 1998, the Delta II rocket lit up the Cape Canaveral sky, sending the orbiter on a 461 million-mile journey. For 9 months, everything went according to plan. The spacecraft cruised through the void, its systems humming, its instruments ready. Every signal received back on Earth painted a picture of a mission on track, a story of flawless execution. What could possibly go wrong with so many checks, so much expertise, and so much riding on success? But Mars is a place that does not forgive even the smallest oversight. And somewhere, hidden beneath the surface of all that confidence, a tiny detail waited, unseen and undetected. The kind of detail no one thought could bring down a spacecraft. For most of its journey, the Mars Climate Orbiter behaved like a model spacecraft. Every system check came back clean. The engineering teams at JPL and Lockheed Martin watched the data streams roll in, each one confirming what they already believed. The mission was running flawlessly. Telemetry packets arrived on schedule, filled with numbers that matched expectations down to the decimal. Temperatures, voltages, and fuel levels all sat comfortably within their predicted ranges. The spacecraft's orientation held steady, its instruments stayed healthy, and solar panels soaked up the sun without complaint. When it was time for a course correction, the ground teams executed trajectory maneuvers with textbook precision. Each burn nudged the orbiter back onto its carefully plotted path toward Mars. After every adjustment, the navigation models lined up with reality. No alarms, no surprises. The software that tracked the spacecraft's position showed a perfect match between prediction and actual telemetry. In the mission control rooms, confidence grew. If you listened in on the daily status calls, you'd hear calm voices, even come with a bit of pride. This was how interplanetary travel was supposed to look. The routine became almost comforting. Engineers trusted their checklists, trusted the numbers, trusted each other. The spacecraft's health reports became background noise, just more evidence that everything was under control. No one was searching for trouble. Why would they? Every sign said the Mars Climate Orbiter was on course, ready to make history. But sometimes, the most dangerous problems are the ones that leave no trace. Not yet. Mars loomed ahead, a red giant waiting for its visitor. In mission control, engineers watched as the clock counted down to Mars orbit insertion, MOI, the moment every interplanetary mission lives and dies by. The spacecraft was right on schedule, racing toward the planet at over 5 kilometers per second. All eyes were on the burn window, a razor-thin slice of time when the orbiter's engines would fire, slowing it just enough to be caught by Mars's gravity. Miss it, and the craft would either skip off the atmosphere or dive too deep. There would be no second chance. The command was sent. On board, the thrusters kicked in for a 14-second burn. Numbers streamed back to Earth: velocity, altitude, fuel. Tension in the room was electric. Every indicator pointed to a textbook insertion. For a few seconds, it looked like another flawless handoff from Earth to Mars. Then, silence. The data feed stuttered, then stopped. Controllers waited, hoping for the next packet. Nothing. The orbiter had vanished behind Mars, as expected, but the radio blackout stretched on. Seconds felt like hours. The predicted periapsis, or closest approach, should have been 226 kilometers above the Martian surface. Instead, calculations showed something impossible. The craft had dipped to just 57 kilometers, deep inside the upper atmosphere. That altitude was a death sentence. Engineers stared at their screens, searching for a glitch, a missed signal, any sign of life. But every model, every line of code, agreed Mars had swallowed the spacecraft whole. $125 million, 9 months of travel, and years of work, all gone in a matter of seconds. No explosion, no fireball, just a vanishing blip in a room full of stunned experts. How could this happen? NASA did not waste a second. Within hours of losing contact, a formal mishap investigation board assembled in Pasadena. The boardroom filled with engineers, software leads, and flight controllers, each one called in to answer a question no one wanted to face. How does a spacecraft worth $125 million just disappear? Every scrap of data was ordered up for review: telemetry logs, thruster commands, navigation models, even voice recordings from the control room. There was no sign of hardware failure, no hint of sabotage, no explosion on the monitors. The spacecraft had simply vanished, leaving behind a trail of numbers and a room full of experts who suddenly doubted everything they thought they knew. The search for answers began with the basics. Did the engines fire as planned? Did the navigation software send the right commands? Teams split into subgroups, each chasing a different theory. Some suspected a hidden glitch in the thruster system. Others wondered if a micrometeoroid strike had knocked the orbiter off course. A third group combed through the Deep Space Network logs, hunting for any missed signal or corrupted packet. The investigation board demanded simulations, cross-checks, and replays of the final moments. Every lead brought more questions. How could every system check out, yet the spacecraft end up 170 kilometers lower than planned? The deeper they dug, the stranger the puzzle became. The numbers did not lie, but they did not add up either. The answer didn't come from a hardware failure or a cosmic accident. It came from a number, one that should have been multiplied but wasn't. In the heart of the investigation, engineers traced the problem to a single file, the Small Forces data packet. This file, generated by Lockheed Martin, listed thruster impulses in pound force seconds, but the navigation software at JPL expected Newton seconds. The difference? 1 pound force second equals exactly 4.44822 Newton seconds. That's not a rounding error. That's a 4.5 times difference, hiding in plain sight. How does a spacecraft that cost $125 million get undone by a missing conversion? The software didn't just mix up the numbers. It took the impulse values straight from the file, never applying the 4.44822 factor. Every time the orbiter's thrusters fired, the calculations were off by that same multiplier. The navigation code assumed it was working in metric, just like every other piece of data in the pipeline, but the raw numbers were still imperial. The parser's comment even said, "Assume SI." No one noticed the unit flag, no one stopped to ask if the numbers needed to be scaled. The result was that the force applied was only a fraction of what was needed. Commands meant to nudge the orbiter gently into place were too weak by a factor of more than 4. The predicted orbit was a fantasy. The real path cut straight into the upper atmosphere, all because a simple multiplication, one that should have happened at the very start, never did. The math was right, the units were wrong, and that was enough to bring down the entire mission. The Mars Climate Orbiter wasn't lost because of a single person's mistake or a rogue line of code. The real story runs deeper, through the cracks in the system itself. Responsibility for checking the numbers was split between two teams, each assuming the other had verified everything. Lockheed Martin produced thruster data in imperial units. JPL navigation software expected metric. The interface control document listed both, but no one held final ownership of the conversion. The checklist for software validation skipped a scenario that would have caught the mismatch. The only place the conversion happened correctly was in the simulation scripts, never in the pipeline that flew the real spacecraft. Pressure to meet the narrow launch window meant change requests were fast-tracked, and some were closed without a full review. Engineers trusted in process and precedent, not in double-checking the basics. The culture prized speed and efficiency, sometimes at the expense of rigor. No end-to-end test ever ran with the exact data flow that doomed the orbiter. What looked like a rock-solid system was, in reality, a patchwork of assumptions and handoffs. The loss wasn't just a math error, it was a warning about what happens when no one owns the details. In a world where the smallest oversight can erase $125 million overnight, the lesson is clear. Every link in the chain matters. Right now, billion-dollar missions still hinge on details as tiny as a line of code. As we reach for Mars and beyond, perfection isn't optional, it's survival. In space, the smallest oversight can erase everything. Precision isn't just technical, it's existential. What margin for error are we willing to risk?